I'm going to be presenting on an actual modeling approach that we use to predict the magnitude of post-fire increases in flooding. So we're going to go to the immediate response to a wildfire, and I'm sure that's on a lot of people's mind right now with the massive Caldor fires and Dixie fires. Is, what can you do immediately following the fire to prioritize resources? So to approach this, we're going to first look at what is the public agency wildfire response, and I think that's a kind of great dovetail from John's talk. And what do the public agencies already do, and then get into a kind of more detailed modeling approach, how we actually represent fire in these models and represent an increase in peak flows. And then we're going to look at a case study from the Ulatis system, which is near Vacaville, California. And it's actually some work we did last year in September following the Lnu lightning complex fire. So why do we need to evaluate an area after a fire? Well, wildfire alters the landscape and it can cause severe loss of vegetation, and then that leads to severe soil erosion, decreases of water quality, and oftentimes flooding. And as we've learned from many of these recent unfortunate events is, there is this severe risk of debris flows and flooding that needs to be effectively communicated to resource managers. But these fires that we are dealing with now are absolutely massive. So there is kind of a question of, following one of these fires, how do you prioritize resources to look at areas that are in immediate danger and prioritize to the areas that have had the most severe burning and consequently might have very severe post-fire flooding. And we want to direct these resources to the vulnerable locations where there's critical infrastructure and use that to inform our monitoring and try and kind of prevent some of these catastrophic events to the extent we can, or at least inform the public. So in California, there's two kind of major sets of teams that immediately respond following a fire. There is the burned area emergency response teams. This is a federal partnership between primarily the Forest Service and the National Park Service and many others. And following many major incidents on their lands, they send a group of teams to evaluate the fire. So that includes engineers and hydrologists. There's also the California Watershed Emergency Response Team, or WERT team, that's primarily led by CAL FIRE and the California Geological Survey. And both these groups, following any fire, there will be remote sensing analysis of the fire, even as the fire is happening, to look at the areas that have burned. This burned area is classified into areas that burned at high, moderate, low, and unburned, so we can just understand the extent of the fire. And then following the fire, field teams will go out and verify these areas, and they'll create what's called a soil burn severity map. And this is really important because we're going to use this soil burn severity map. It's going to classify all of the areas by the severity of their burn. And we're going to feed that into a modeling process to help inform where we're going to see the largest post-fire increases in peak flows. So some of the products they created, and this is from the Lnu Fire, is they do an assessment of peak flow multipliers. So that's saying which areas, what they think the magnitude of potential increase at specific point locations. And I've called out where Vacaville and Ulatis system that we're going to be looking at in greater detail is at the bottom. There's also an effort to model debris flows. This is usually done by the USGS following many major fires. And then the California Geological Survey goes in and assesses many of the values of risk following fires. So they will go evaluate each building that's burned down, or buildings that are potentially in the fire zone or critical infrastructure. And all of that is really important information, but there are some areas where there could be more information added, and there are some data gaps that could potentially be filled in. So the kind of CAL FIRE and the WERT team and BEAR team responses is intended to be scalable and deployed at these really large spatial scales. So they don't always rely on local data sets, assessing if there's a local hydraulic or hydrologic model that has already been created. And they aren't intended to be to the degree that you would use them for design. And oftentimes the results are not available at kind of the exact spatial resolution that you would want to evaluate an area. And this is kind of where we came in for the Ulatis system, where the kind of primary area where they were concerned about flooding was a little bit outside of the extent of the pour points evaluated in the report by CAL FIRE. And it's also just really important to communicate these results and have many voices echoing them so that the kind of message of risk can be communicated effectively to the public. And I will note this is very much a immediately response as opposed to a kind of larger scale planning approach. So I'm going to take a brief aside and we're going to dive into the science of what happens following a fire, and then how we're going to feed it into a model. And then we'll look at how that model was applied to the Ulatis system last year in this post-fire case study. So following a fire, the most obvious thing is the canopy layer is removed. This takes away all the trees or potential vegetation would intercept a lot of the rainfall. And that vegetation, with it gone, it loses its buffering capacity. That's important to represent this huge impacts to the soils. So the soil structure can be collapsed. Hydrophobic soil layers can be created. There's a reduction in porosity, and all of these contribute to decreasing infiltration rates, meaning that when we get a large rainfall event after a fire, we're going to get a lot of runoff. And we've also just removed all of the ground cover, so we've exposed bare soil. So we have basically reduced the roughness on the hill slope, which means that when we get rainfall, we're going to have the water running off very quickly and not infiltration, which can lead to these post-fire flooding events. So we're going to look at two separate models that are going to kind of give us a bigger picture of how we can represent post-fire increases in peak flooding in a modeling framework. So on the left, we have the soil and water assessment tool. This is a very widely used model that is applied at very large basin scales. Models can be done for the entire United States. It's a continuous time water balance model. So it's actually relying on the curve number method to predict runoff, which makes it easy to run for very large scales, but it has some limitations in representing certain physical processes. The other one we're going to talk about is the kinematic runoff and erosion model, often referred to as K2. And this is a physically based event-oriented model. So it's set up to more to run design events, and it describes the physical equations that govern hydrodynamics and infiltration with the soils. So this is much better suited to small watersheds. And this is actually what we're going to apply in the case study. So in this case study, we use the automated geospatial watershed assessment tool. And this program can use both SWAT and Kinematic 2. And a portion of it has been calibrated based on a lot of existing studies to represent fire. So within the SWAT modeling framework, we're going to look at changing the curve numbers in the model. So by changing the curve number, you can change the amount of runoff. The benefit of just changing the curve number is it's a quite simple process to do, and it's backed up by a couple of studies where they've looked at pre-fire and post-fire in certain watersheds and then calibrated that curve number to those specific events. And we can apply that information very easily in a model. A limitation of that approach is that by just adjusting the curve number, you're not able to actually predict the volume of runoff that's coming off of one of these events. You're only able to kind of adjust it to hit the peak flow correctly. But it's less well-tuned to actually representing the physical processes that are happening following a fire. So in Kinematic 2, it's more of a process-based model. So it represents what's considered Hortonian flow or infiltration excess runoff, where we get so much rainfall that it cannot infiltrate into the soils. And this is actually the process that we observe a lot of times, especially in the Southwest following a fire, where a lot of the ground cover has been burned away. So we are basically representing a scenario where we have this kind of highly altered soil and we get a rainfall event, and we are modeling the amount of that rainfall that's going to run off directly following the fire once its infiltration is very limited. And in Kinematic 2, we can represent a couple of these different processes and how they change following the fire. So we can model the interception. So that's the amount that trees can intercept following the fire. The infiltration processes, directly modifying the soil properties within a spatially distributed model. And then we can modify the Manning's roughness to represent a fire. And this is gonna help determine the rate at which the water will run off over the hill slope. And these have also been calibrated to pre and post fire events, primarily in southwestern watersheds. So this is an example that we actually applied in the Ulatis system following the Lnu Fire, where many hydrologic models, you input what's considered a land use layer. So this is the National Land Cover Database. And for existing conditions, it represents whether the existing ground is shrub or grassland or a number of different categories. And that's usually how the curve number or these other parameters are defined in the model spatially. Following a fire, we can input the burn severity layer and say which areas burned at high, moderate, and low severity. And for each of those land uses in those specific locations, we can modify the physical parameters in the models. So for a SWAP model, we would modify the A, B, C, and D, which are the curve number. And then for a physically based model like Kinematic 2, we would modify the cover, the interception, and the Manning's roughness, depending on the severity of the fire. And that's done, can be done using the land cover modification tool within the automated geospatial watershed assessment tool. That's a lot of acronyms. So now we're going to take a look at this case study for the Lnu Fire. So the Lnu Fire was, I think, the 6th largest fire in California's history. So it covers an absolutely massive area surrounding Lake Berryessa in Northern California. And, after this fire burned, there was this immediate question of, all the agencies are gathering together. Cal Fire put together this great report doing some of the modeling. But there are more specific questions that needed to be answered, in particular for the Ulatis system. The Ulatis system is a flood control area that leads through the city of Vacaville. And they've had historic issues with flooding that were not related to the fire. So the watershed actually flooded quite extremely in 2002 and 2005. And following that, they had done a lot of work. So what we were tasked with doing is working with Solano County Water Agency to help provide a higher resolution look at how this fire happened in the hills above Vacaville would affect the water that's flowing through their system. So there's a couple of major creeks that move through the system, the Ulatis Creek and Alamo Creek, both of which flooded back in those 2002 and 2005 events. So luckily, we were able to rely on some existing data. A lot of work can be done in this Ulatis system drainage study created by West Geos back in 2008. This was done in response to the previous flooding events. And they had set up a calibrated hydrologic model for 10 and 100-year events. The other thing they had done, which was extremely helpful, is they had evaluated within a hydraulic model the channel capacity at various points within the system. So for the primary creeks, you can see on the top left Ulatis and then Alamo Creek. Along many critical crossings, they have the channel capacity, so we can look at this and kind of understand what type of channel capacity or what type of flows might cause a problem in that system where we exceed the channel capacity following a fire. And they had also modeled the 10 and 100-year events. So we developed the cbec team, so myself, Luke Tillman, and Chris Bowles, developed a Kinematic 2 hydrologic model for the system. So this is done in a fairly automated GIS process where we delineated the watershed that you can see in the map there into 153 catchments. Over each of these catchments, we're modeling these event-oriented simulations where we can look at runoff and actually erosion and sediment transport within those catchments. We parameterized it using kind of best professional judgment and the land cover, soils, and the post-fire land cover to modify burn severity. So this uses the NRCS Cisurgo soils data, gets fed into the model, and then the 2016 land cover. And then the post-fire soil burn severity had been completed weeks before. And we did this in the kind of month or two following the Lnu fire, so immediately after. All of these models are based on these design storms. So what we represent is a series of 24-hour design storms using the SCS Type 1A storm distribution. And all of these 24-hour events were over the kind of threshold, the highlighted cells in red were over the kind of immediate durations or precipitation thresholds used to define debris flow warning triggers. Yep. And this was a very kind of immediate task right after the fire, so we wanted to do this as quickly as possible, but we also wanted to make sure that the results were accurate and usable, so we did some limited calibration to make sure we were representing the hydrologic system well. So this is a comparison of a number of analysis points where we were evaluating flow to points where the 2008 calibrated model had looked at their 10-year event. And even with this very quick model that we didn't have to spend lots and lots of time calibrating perfectly, we were able to represent runoff quite well. At the confluence where the water flows out of the system, our average air for the peak flow was only off by 4%. So it was a fairly accurate model in representing these design storms, even without going through and doing the substantial calibration process that would take a long time. And for each of the points, these are kind of key locations where we wanted to evaluate flow. We ran, so for the entire model domain, we ran 64 different simulations representing unburned and burned conditions in the watershed and a number of different event depths. So what we're going to see is the results from each of these analysis points. That's where we have the blue check marks and the numbers. And I'll just kind of show you an example of what that looks like. So each of these tables is a series of simulations where we represented different 24-hour design storms, ranging from 2 inches, so very little, to a very large event, which would be 9.6 inches of water in 24 hours, and all distributed by the SCS Type 1A distribution. And for each of these, we modeled pre-fire and post-fire. And since we don't know the exact conditions of the watershed before a fire, we varied the initial watershed conditions. So we used the soil saturation, the initial relative soil saturation, which is the percent of the porosity that is taken up by water before you start your rainfall event. So how full of water is the soil already? So it's probably likely that if you get a major atmospheric river, you're kind of on the higher end of saturation of the watershed, unless you got a storm, while the watershed was relatively dry. And for each of these events, I'm going to go back up to this previous figure. We can see the pre-fire, those lines in blue for the different relative saturations, and the post-fire. And we can pull this information out for any particular location. And these are the results for Alamo Creek. It's starting at the upstream area, and you can see in the red on the right, you have the post-fire response where the water actually runs off quicker. It's a much sharper peak. And then it actually falls below as we get into the later time. The time is in hours there. It actually falls below the existing conditions because the water is flashing through the system much quicker. And we can see how that flood wave moves through the system for this 24-hour event as it moves downstream. We can also look at some other areas, and this is going from a creek that burned very poorly to the kind of whole watershed at the bottom. On the bottom left, we can see the results where the water kind of goes out towards the delta. And you can see that the increase in post-fire peak flows is very muted since a lot of the area in the watershed was not burned severely. a lot of the burning happened at the top of the watershed where we had the largest post-fire increases. And we can also see the sediment and change in actually sediment flux coming out of the different streams. These are the results for Ulatis Creek for both sediment and discharge. And then here's how we can interpret this at the watershed scale. We see in those upper watersheds, we're seeing this major increase in peak runoff. This is because in those watersheds under normal conditions, you probably wouldn't generate a lot of runoff. While post-fire conditions, we are generating a lot of runoff since we've burned off all of that vegetation. And you can see as you move down in the watershed, you see less of an increase in the post-fire peak flow. Same thing is true for sediment, except you see an even larger increase in the post-fire peak flows. And then kind of to wrap this up, what can we do with this type of information? Well, the really great thing is that we have the channel capacity in all of these different locations, so we can use this to inform our prioritization of where we would want to immediately look at. So we identified a number of areas where there is a threat due to the fire, primarily in the areas that were kind of downstream of the high severity burns. And what we can do is we can look at a particular location and say for a pre-fire event, we generally understand what the discharge would be for certain types of rainfall events. So if we have 4 inches of rainfall pre-fire, we're probably not going to generate enough water peak flow to exceed the capacity of the system. However, 4 inches, that's roughly a 2-year event in this watershed following the fire, if the soil is relatively saturated, could cause a peak discharge that was in excess of the channel capacity. So that would be extremely worrisome if they were to have had a 24-hour event with 4 inches of water last year. Luckily, it did not rain a lot this last year. So we didn't actually get to observe whether this occurred or not. There was very little rainfall directly over the watershed. And this kind of information is really important to kind of pull out the exact spatial resolution and look at the different kind of areas we want to evaluate, identify where our risks are, and then kind of come up with a plan to monitor and potentially mitigate any adverse effects. So we identified key drainage infrastructure in areas where you could potentially monitor, areas where the channel conveyance is limited, and where you would probably want to monitor before and after each rainfall event in the year to make sure you still have at least the same channel capacity and you're not kind of filling up your stream and causing a problem where you would potentially overtop the banks of the system. And this was a really interesting study, and we'd like to thank Solano County Water Management Agency for working on this project with us and contributing all of this information. If anyone has any additional questions about this type of work, feel free to reach out to myself or Luke Tillman, who also was doing a lot of the modeling on this project. And with that, I think I am ready to open it up for questions. Thank you so much for listening this late in the day.
Thank you, Michael. That was a great presentation. I haven't seen any questions come in. I'll ask Allison if there's anything getting typed up right now.
Nope, nothing was sent in that I can see.
I will offer once again my own observation that those curves you showed, those runoff curves, were very dramatic in how much increase there was in the peak flows. But also what occurred to me is that the volume increased, 4 or 5 times too. So that's just an indication of how little water is being retained or buffered up on the hillsides, either through just retention on the foliage or infiltration in the ground. And it's just a very dramatic result that you got through your modeling.
Absolutely. And those kind of upper areas of the watershed burned incredibly severely. I had a chance to look at them, and it was just, there was very little up there. Whereas the areas that burn at kind of low and moderate severity, I think recovered somewhat quickly. But those high severity burn areas, it is not shocking to imagine that they would kind of have that large of an increase in peak flow. But it is a relative increase in peak flow. So it's comparing a very large number of runoff to a very small number, because those watersheds typically wouldn't generate a ton of runoff when they have, plants and better infiltration to buffer a storm rainfall event.
Yeah, it'd be interesting to see how those curve discrepancies progress over the next couple of years as the burn area starts to recover and revegetate, and to see how long those impacts last. And I'm sure it's several years.